Okay, so here we are for chapter 10, and we are going to talk about the visual system. Once again, uh, just like the first chapter of this unit, chapter 9, it's normally done in 3 sessions, but I'm going to go over it in 2. And I think I've sort of figured out a plan for the graphics that don't work. I know I told you last time that if you scroll down to the pages that I made for my online biopsych class, it has all of the slides and the pictures down there. So for any slide where it's missing, I think I can just go over to that page since I'm sharing my screen and show you the missing picture. And just also it shows you that it's there. So this is chapter 10. We have light and visual apparatus, color vision, form vision, and then perception of objects, color, and movement. To break up the monotony, I will structure this into lectures. So I will do light, tracing it through the eye, and color vision theories, and then form vision and perception will be the next one. So bear with me as we go through this journey. Just a reminder that after chapter 10, which is this week, we will have a quiz. So the third quiz will be available next week. I'll open it up on Monday on chapters 9 and 10, and then you will have until, I guess, Friday to take it, which is after next week, obviously. And the exam will be the following week because you'll be doing chapter 11, going over chapter 11 as you, the week you're taking the quiz. So looking at what we see, one of the things I wanted to point out from chapter 9 is the fact that what we see, what we hear based off of chapter 9 is the range that you saw for the auditory system was about 15 to 20,000. 15 itself, not 15,000, but 15 to 20,000 hertz as far as pitch perception, which means that things that go above that or things that are below that sound, our ears cannot hear, not without help. Well, this is something very similar in the electromagnetic spectrum with respect to the visual system. What we see are basically shorter or longer wavelengths, just like how we account for higher or lower pitch. Remember that in chapter 9, I talked about it as the color that we perceive. So the shorter wavelengths are going to give you a more blue purpley ones down near 400 nanometers. And the wavelengths that are up above closer to 700 nanometers or 800 nanometers is going to give you a really red tint or hue. So is it possible, and this is for another time and another discussion, that maybe things like ghosts we don't hear or see because they're not part of our spectrum that our brain can interpret? It's possible, but again, I'm a hard science person, so you're going to really have to convince me. But I guess, there's an argument to be made. So as you see here, what we're actually seeing as far as visible light, which is the adequate stimulus for the eyes and for vision, is only about 1/70th of the entire spectrum. In fact, radio waves and waves that, that create sound waves we can hear that come from radios and things like that is actually part of the same spectrum. So looking at the spectrum here on the left, you see gamma rays and X-rays are below the wavelengths needed for what we can see or perceive as colors. Gamma rays are things we can't see without a special machine. Obviously, X-rays you can't see. You just know that you have to put on that lead vest to protect yourself, and you can't see X-rays without putting them in a specific machine. UV rays are bad for you. They are ultraviolet rays, provided by the sun. This is why you're not allowed to, or you shouldn't, look directly into the sun. And we know UV rays are harmful because we are protecting ourselves using sunglasses. We're protecting our eyes. And for our skin, we're using sunscreen. You know, that whole SPF thing? Yeah, you're trying to protect against sun damage from UV rays, even though we can't see them. Uh, just above the spectrum of nanometers is infrared rays, which you need special night vision goggles for. So, you know, consult the military for that. And then looking ahead and looking even higher up, we see radar, FM, TV, AM, and then AC circuits. So all of this is on the same electromagnetic spectrum. We can perceive stuff on TV signals if it's turned on, FM and AM if the radio is turned on, and things like that. So what we can actually see is limited by our brain because our brain can only interpret around 300 to 800 nanometers of light, which is our color spectrum, including black and white. So just like we went over the eyes, we went over the ears in chapter 9 and the outer ear, middle ear, inner ear, and that whole pathway. The eye itself is a little less complicated, but yet not easy. So the first thing we want to do is take a look and see what the parts of the eye are, kind of like we did with the ear, and where this signal is taken and how it's, remember we use the word transduced, how it is transduced from a physical signal of light waves that enter the eye and how it gets converted or transduced into a neural signal that the brain can interpret. And of course, like we did in the auditory system, we are going to follow the visual system and see the pathway that it takes to the brain from the eye. So the eye here, as you can see, is concentrating on looking at a pencil, and the pencil has the eraser side up and the point side down. Now, one of the first things, before we even go over the parts of the eye and things like that, I want you to notice that the image from our visual field that goes through the eye and all of those parts is projected onto the back of the eye in this big area that you can see with a red box called the retina. But the weird thing about this is that the image is upside down and inverted like a mirror. So you can't tell the inverted part because you're just looking at a thin pencil, but you can see that it is inverted in that, or upside down, in that the eraser now, when it's projected onto the back of the eye, like, you know, like a movie projected onto a screen, the eraser is now on the bottom and the point's on the top. If this were words on a page or something like that, the words would show backwards, like you were looking in a mirror. But the interesting thing about that is, even though it's projected to the back of the eye upside down and backwards, by the time that message and that information travels up through the sensory system of the eye to the brain, when it's perceived and the big picture is put together, of course it's right side up and the right way around in our interpretation. So when it's projected onto the eye, it's upside down and backwards, mirror image. And when that information gets projected to the brain, we see it right side up as it is in the world. Interesting, right? So let's look at the parts of the eye. Well, first we see the outer layer, which is sort of a protective covering of the eye on the very outside, even before you get to the pupil or the iris or anything like that. And that's called the cornea. You can see that word closest to the pencil out there. The cornea is an outer cover. It's a protective layer of epithelial cells in the eye that just serves, again, as protection. So in this case, I don't know if anyone's ever scratched their cornea. I actually have. It was a dodgeball accident where somebody threw it from the opposite corner, and I did not catch it in my peripheral vision because, well, full disclosure, it was what we call a jamboree, which was like before the season started. So instead of your regular 10 on 10 or 12 on 12, it was like 20 on 20 or more. So it was pretty crowded, and the ball came at me from an angle. And so normally, you know, your eye does this thing where if there's anything coming close to it, not only does it have the cornea, but you usually are able to blink and, you know, protect your eye. I was not so lucky. So I ended up having to wear goggles after I came back, but I couldn't play for like a month. So cornea, scratching it is no fun, trust me. But at least it helped protect my eye. There was no eye damage whatsoever. On the inside of the eye, we know the colored part and we know the black part, right? The black part is called the pupil. And what the pupil does is basically it adjusts itself. It gets bigger or smaller, and no, not depending on the drugs you take, although yes, that can happen as a byproduct. But what it does is it expands and contracts in order to let a certain amount of light into the eye. So when does it do this? The black part of the eye, the pupil, opens up when you're in relatively little light because it needs as much visual information from light as possible. So it gets bigger the less light there is. You ever wonder when you're coming home late from going out, remember those days? And you are trying to kind of sneak back in the house. It's kind of late. You don't want to wake anybody up, whether it's parents or roommates or whoever. And you're just kind of fumbling around in the dark, hoping that you can get your night vision going and that you don't hit your shin against the coffee table and, yell out and wake everybody up. Well, after about, maybe a minute or so, you get your night vision about you and you're able to kind of see at least the outline of shapes and forms in your house or apartment. That would be your pupil opening up to allow as much natural light as can be, enough for you to at least navigate through your house and get safely to your bed. When you come out of remember movie theaters? When you come out of a dark movie theater during the day and it's really bright outside, that's when your pupils tend to shrink because that's way too much light information that we need. So they tend to shrink and you kind of squint until you get used to it and or put on some sunglasses or something like that. And the pupils get smaller because there's already so much light coming in that we don't want to, blind ourselves or, over account for all of the light because then you won't be able to see anything. So the more light there is, the less we need to be able to understand what's going on in our world. And there you go. So what allows this to expand and contract? Well, we also have the iris of the eye, which is your colored part of the eye. That's the one that you call, the one that we say, oh, you're blue-eyed, you're brown-eyed, you're green-eyed, right? In this sort of cross-section, it kind of looks like green, hazel eyes. Does that serve a purpose or is it just a pretty color? Well, apparently it serves a purpose because what the iris does is basically controls the pupil expanding and contracting. So it's the iris of the eye, the colored part, that controls the black part of the eye and how much light it lets in to the eye that projects onto the retina. At the bottom, you kind of see a ciliary muscle. That ciliary muscle on the bottom is not attached to the iris or the pupil, but it is controlling the lens and allowing it to focus. And that brings us to our lens. Well, just like the lens of a camera, as you probably imagine, or if you had me for Psych 1, as I taught in Chapter 6 of Psych 1, the lens is like the lens of a camera that focuses the image of light, goes through the pupil and projects it onto the back of the eye, which is that big area called the retina. A lot of times the lens can't focus itself even with the ciliary muscle due to many factors. And so you may have to reflect a different lens on top of that to compensate and make the picture clearer. I do this by wearing glasses, as some of you do, and some of you wear contacts, which is just a way to do it by placing a little lens on top of the eye ball, right basically on top of the cornea, and that way you don't have to worry about glasses. But I was never able to master the art of easily taking out and putting in something on my eyeball, so I stick with the glasses. Much easier for me. So those are the parts of the brain. Sclera is sort of this gelatinous stuff inside the eye that kind of keeps it, I know that people hate the word moist, but not dry. How about that? And then the rest of the time, we want to concentrate on that area in the back of the eye called the retina, because that's where the receptor cells of the visual system are. There's about 3 main layers of cells and a couple of helper layers that convert this information from the visual system into a neural signal, action potentials, chemicals, things like that, that the brain can then interpret. In the auditory system, for review, we had in the cochlea, the inner ear, we had those hair cells, which were the receptor cells, and those bent and gave off basically action potentials that turned into chemicals at the end of the auditory nerve. Well, here we have cells in the back of the retina called rods and cones, or photoreceptors, that basically give off a chemical in response to light hitting the cell. And that is what transduces or changes or turns the physical stimulus of light waves into a neural signal. So in the back of the retina, there are 2 things I wanted to point out. Number 1 is an area right sort of in the middle of the retina, towards the very back of the eye, called the fovea. And the fovea is the point of central focus. So I talked about that there are 2 types of photoreceptors. There's rods and cones. Many, many more rods than there are cones. And cones seem to be concentrated, 95 to 99% of them, right there in that fovea. So they seem to be responsible, and we'll go over this a little more, responsible for the picture being nice and clear and you being able to focus, your eyes being able to focus on something. The other thing I wanted to point out is this area called the blind spot. And the blind spot is an area in the retina, and you can see that the retina goes all the way down on the bottom and all the way up on the top, everywhere but sort of the front where the pupil, iris, lens, cornea, all of those are. Everywhere else seems to have layers of retina in the around the very perimeter of the back of the eye. But there's one area called the blind spot here where basically, this is where I would ask you guys, why do you think it's called the blind spot? And this is where maybe some of you remember from Psych 1 if you had me. But the blind spot is the area in the eye where there is nothing projected. So it is part of the retina area, but there's no picture projected there. And the reason for that is because, much like the hair cells, axons, came together to form what we call the auditory nerve, there's a layer of cells in the retina called ganglion cells. And those ganglion cells are the ones whose axons form not the auditory nerve, but the optic nerve that you can see that leaves the back of the eye and heads out to the brain. The part where these axons are leaving the eye is called the blind spot, because there are no retinal cells in that area. It's all the axons of the ganglion cells that are sending the message to the brain. So we have the fovea, or point of central focus, in the retina, and we have the blind spot, which is where the axons of the ganglion cells come together to form the optic nerve and bring that information to the brain. So we have 3 main layers of cells. I'm going to point out that there are 2 sort of helper cells in here, but we're not going to really worry about them for this class. If you are in a 4-year college and taking biopsych for upper division, senior level, then maybe. But for the purposes of this class, we're going to try to keep it, you can't keep it too simple, but we're going to keep it, not too complicated. How's that? So looking at the back of the eye, if you were to zoom in on the layers of the retina, you might think that the layers were in reverse, because light is going to hit the layer, right? Light would be hitting the layer closest to the eye, not farthest back. However, the way that it works is that the layer in the very, very back of the retina, the one at the very back of the eye, is those receptors, those rods and cones, which again are named what they look like. So you can see that in the very back of the eye, this purple layer is the rods and cones, which are going to give off a chemical when they're hit with light waves. And that chemical is going to activate the next cell, which are called the bipolar cells. Now, what bipolar cells are actually doing, and I don't want to get too confusing, is they're inhibiting the ganglion cells from firing. So the bipolar cells are telling the ganglion cells not to fire. And it's when the rods and cones activate and send chemicals to the bipolar cells that the bipolar cells then, and I think you remember this word from earlier in the class, disinhibit the ganglion cells. So when the bipolar cells fire, it causes the ganglion cells to take that information from the rods and cones and send it out the eye, right? Remember, it's the ganglion cells, axons, that form the optic nerve that leave out of the blind spot of the eye. So, looking at the picture on the right, we see that rods kind of look like a rod, and cones kind of have that cone shape in their receptive fields at the top, right? So 1, 2, 3, 4, 5 of those are rods, and there's 2 cones in there. The rods and cones, when light hits the rods and cones, their natural reaction is to give off a chemical. Rods give off a chemical called rhodopsin, and cones give off a chemical called iodopsin, which then gets transferred to the bipolar cells, and the bipolar cells then disinhibit and give that information from the rods and cones to the ganglion cells. So the rods and cones are receiving the information from light waves, turning it into a neural signal, and basically giving that information that they have to the ganglion cells. And the ganglion cells, as you can see on the bottom, right, our ganglion cell axons are forming together into the optic nerve and leaving the back of the eye headed to the brain. So the ganglion cells take the information from rods and cones about visual information, and the ganglion cells are the ones that give that information to the brain. So let's look at these rods and cones. So again, we had outer hair cells and inner hair cells in chapter 9. It was the outer hair cells that actually converted the signal. And for review, the inner hair cells were the ones that sort of sharpened the sound. For the rods and cones, we have the rods, which are much more numerous. When rods are hit with light waves, they give out or secrete, release rhodopsin. Now, the thing about the rods that we already talked about, or I already mentioned, is that they are way, way more numerous than the cones. And they're spread out all along the periphery of the retina. They function best in really dim light, poorly, or not at all in bright light. So if it's really bright, you're not actually getting the rods to function. That's the cones. If it's very black and white, fuzzy, again, I use the example of, sneaking back in the house after midnight and just trying not to hit your shin on the coffee table. So detail vision is poor. You can't see colors, but what you can see is shapes, outlines, and a lot of times, because when our brain detects movement, we're seeing something moving amongst a still background. It also helps for seeing motion. So black and white, blurry vision, form, outline, shapes, and motion. The receptive fields, again, location is mostly in the periphery of the retina, not located. We don't see rods located in that fovea in the center. We only see cones there. So when we look at the receptive fields of these rods, they're very large. Why do they only give a very fuzzy black and white sort of outline, light sensitivity picture to the ganglion cells? Well, if you think about it, right, there's a lot less cones. So the cones are basically forming a very specific connection with the ganglion cells. It's like a 1-to-1 or a 2-to-1 connection. So it's a very sharp picture. Where with rods, it could be, 100 or 1,000 of those rods that are giving their information to one ganglion cell that's sent to the brain. So you're not going to get a very clear picture if you have hundreds or even 1,000 of these that are contributing to one ganglion cell. So light sensitivity, dark light, yes. Shape, outline, form, yes. Motion, seeing something moving, yes. But the rest of your vision, all of the clear stuff, is the cones. So the cones give off their own photopigment, which is not rhodopsin. I like to think of the nice way to remember it, rod rhodopsin, rod rhodopsin. And then cones are the other one. You just have to remember iodopsin, which kind of sounds like iodine. So that's how I remembered when I was in school. So Cones, when hit with light, give off iodopsin, and that functions best in bright light. Does not function very well in dim light. That's all the cones. In brighter light, that's all the rods. In brighter light, that's all the cones. Cones, I like to say, and if you had me for Psych 1, you may remember this now, but cones are the 3 C's. Cones equals clear, meaning clear vision. Cones equals color, because it's the cone system is what distinguishes among the colors that we perceive. And as you see, the location is mostly in the fovea and surrounding areas. So that's the center of the retina. So cones equals color, cones equals clear vision or clarity, and cones are located mostly in the center of the retina. So the cones I like to think of as the 3 C's. Cones equals color, cones equals center of the retina, which is the fovea, and cones equals clear picture. So the receptive fields of the rods were really large, with many of them converging onto one ganglion cell. That means that you guessed it, and you read it, the cones have very small receptive fields, with maybe 1 or 2 converging on a single ganglion cell. So this contributes to very detail-oriented vision. And the reason for that is it's very clear when you have a 1-to-1 connection with cones and ganglion cells, or even a 2-to-1 connection. You're giving a lot of information that's very specific. With rods, they're just given a little bit of information from each one to ganglion cells, and the ganglion cells kind of report that to the brain. But it's a very small receptive field for cones, with 1 or maybe a couple converging onto one ganglion cell, and this is how we can see a lot of detail and clarity in our vision. So we're looking at 2 sort of rows, as you can see in there. The 3 main layers of cells are the rods and cones, the bipolar cells, and the ganglion cells. Well, on either side of those, from the rods and cones to the bipolar cells, we see helper cells called horizontal cells, and we also see between the bipolar and ganglion cells, we see these ones called amacrine cells. Again, it's all about that when there's no visual information, it's sort of inhibiting the ganglion cells and the bipolar cells, and then that sort of reverses when light hits. So the horizontal and amacrine cells are really just helping to disinhibit. They're helping to keep the signal nice and clear. But we're not really going to get into that, and I'm not going to test on it, so don't worry. So you can see that in the bipolars are released from inhibition when the rods and cones give off that chemical, and it stimulates the ganglion cell to be able to send that information from the rods and cones to the brain, and we can get a reading of what it is that we're seeing. The area of the retina from which a ganglion cell receives its input, so from the rods and cones to the ganglion cell, where the input is received is called a receptive field. And as I already talked about in that little table, the receptive fields of cones are small because few are attached to each ganglion cell. And actually within the fovea itself, where we have about 95% of our cones, each cone has its own ganglion cell. So you're getting a very specific 1-to-1, 100% of the information is going to this ganglion cell in the fovea. As a result, we have a very clear picture, which we call visual acuity. This is the ability to distinguish details. We can look at the difference in colors. We can look at the difference in shapes. We can look and see if there's very fine details that we can distinguish. Of course, this is greatest in the fovea, and the farther away you get on either side from the fovea, the less clear the picture becomes because it's all rods and no cones. So in the rods, again, the receptive fields are larger because many rods share a ganglion cell, so they're only contributing a tiny little bit of information. And this also causes sensitivity to light, but more of a blurry black and white picture because it reduces your visual acuity when there's so many rods that are going to one ganglion cell. So we see the rods really, really numerous in the periphery all around the retina, except for the fovea where there's basically none. Now here is one of those examples that I told you. Sometimes the picture just doesn't come up when PowerPoint was converted to this format for my laptop. But let me just show you. Let me go over the slide and then I'll show you on the course page where it is. So we've already established that there's 3 layers of cells. We have the rods and cones. When light hits them, they give off a chemical. Rods is rhodopsin, cones is iodopsin. That goes and travels through the bipolar cells, which are disinhibited, and that information is sent to the receptive fields of the ganglion cells. Now the ganglion cell axons come together and form the optic nerve, just like the hair cell axons came together and formed the auditory nerve in chapter 9. The optic nerves go out and exit the blind spot of the retina. So we have optic nerves in the left eye and optic nerve from the right eye that head towards the brain. Remember, I said that the brain is cross-wired, but not completely. So majority, 85 to 90% of the information from the left eye will cross over and go to the right side of the brain, and vice versa. So the optic nerves, as you will see in the picture, which we can't see right here, will join and cross over for a short distance. Now there is the area where they cross is before they synapse. So actually for the main visual pathway, there's only 2 stops along the way. And based on what you know from chapter 3, and chapter 9, you probably already know what it is, but we will go over that. So once the optic nerve leaves the eye, the majority of those axons cross over and form an X. 85 to 90% from the right eye go to the left brain. 85 to 90% from the left eye go to the right side of the brain, or right hemisphere. So you see a left visual field to the right brain and the right visual field to the left brain. And the nerves, after they cross over, this area where they cross over is called the optic chiasm. And chi, C-H-I, is Greek for X. So it's basically just the point where the optic nerves make an X as they're headed to the brain. Where they synapse, pretty simple. It's only a 2-step process. They, as we know, 4 of the 5 senses go through the thalamus. As we hopefully recall from chapter 9 last week, the auditory system goes through the MGN. Remember, I have an audition at MGN Studios. So that is the medial geniculate nucleus of the thalamus. And now, of course, there's a couple more steps along the way for the auditory system. But for the visual system, we have the LGN, or lateral geniculate nuclei, which are just on the lateral side towards the outside of the MGN. From there, in the thalamus, they synapse. Of course, you know what the thalamus does, relay system and amplifier. So it sends the information from the LGN straight to the occipital lobe and the visual cortex, or what we call V1. So if I were to go over here, I just wanted to show you guys here that chapter 10 visual pathway, right? Here we see the same slide. Ganglion cells form the 2 optic nerves. The optic nerves join at a short distance. So I can't really zoom in, but this is the picture that you'll be able to see. So the left side is A, the visual field. The right side is B. And what we see here is the left eye, majority of the axons cross over at this area called the optic chiasm. So majority of them go to the right. The ones on the very outside, the right visual field of the right eye, stays on the same side. So everything in the left visual field goes to the right side, and everything in the right visual field goes to the left side. So everything in green is in the right, everything in red is in the left at this point. Here in the lateral geniculate nucleus of the thalamus, they synapse, and then they get projected to the visual cortex, or V1, of the occipital lobe. And remember from chapter 3, the occipital lobe only has one job: visual information. All right, so let's go back to the PowerPoint and continue. The fact that we have 2 different eyes, it allows us to do 2 things. Remember from chapter 9 in the last chapter that we talked about the fact that having information from 2 ears converging with those coincidence detector cells allows us to understand where a sound is coming from. So we can hear it first on the left side if it's closer. And remember, it takes a while to get into the right ear, so different phase shift and different timing, different phase in the wave. But it allows us to understand where a sound is coming from. For retinal disparity, where it hits in the retina also helps us to understand how close or far away it is from us. So the fact that the two eyes have information that converges gives us the power of depth perception to know how far away or close something is, which helps us out. If I'm going to hand you a pen and I say, here it is, you know that it's close enough, your eyes can tell that it's close enough to you that you can just reach your hand out and grab it. And that coordinates the visual system, of course, with the touch system. So in the last chapter, we also talked about the where and what stream, the dorsal and ventral streams. And as I promised, we have that in the visual system as well. So things that are more distant, as you can see, farther away in B, are more on the nasal side, towards the nose, towards the inside of the eye or the retina. Closer objects that are really right in front of you tend to be out more on the lateral side or the temporal lobe side of the retina, towards the outside of the eye. And things that are sort of right in the middle are going to be right in the center of the retina. So farther away is projected into a different spot in the retina. Closer is in more of the nasal, outside temporal, lateral side, whereas B would be more on the inner nasal side or medial side. And A is right in the middle between them. So this means that in order to understand things like shape, location, and distance, and to see things in 3 dimensions, not only do we need the visual system, but we also need the parietal lobe, which pays attention to things. And if you remember, in the dorsal stream, it goes up towards that posterior or anterior. Now that we have gone through the main pathway of the eye, which is the LGN, right, from the back of the eye, the optic nerve, to the LGN of the thalamus, and from the thalamus, of course, projected to the visual cortex, or V1. We know that just like deafness, it could come from problems before the information is converted to a neural signal, before it reaches the hair cells in the cochlea, or it could be due to damage between once it's converted and becomes a neural signal and the brain. So for the auditory system, we talked about cochlear implants, which correct the signal. And it's that neural signal that can't make it to the ears, right? Or to the temporal lobe in the brain, to the auditory cortex. So that's kind of what the cochlear implant does. Well, blindness could be due to damage in the retina and damage in the eye. The lens could be damaged so it doesn't project anything. Obviously, majority of the time, if it's in the eye, the rods and cones and those types of cells, ganglion cells, could be damaged. Or it could be damage to the optic nerve, or damage to the thalamus, or the actual visual cortex itself. If the problem is that the signal can't get through because the rods and cones can't transduce the signal, or because the optic nerve is damaged in some way, then much like the cochlear implants, there is a way to restore called the alpha IMS, way to restore vision. So if blindness is due to visual receptor deterioration, so the rods and cones and things like that, but the neural structures that send the signal to the brain remain intact, we just can't transduce the signal, it just doesn't become a neural signal, then we can use these glasses give you, which is an artificial retina. So basically they interpret the signal that is coming to the rods and cones where they would normally convert the signal, and antenna and processor basically turns it into a neural signal, into action potentials and eventually chemicals that send the corrected information to the brain. So in much the very same way that a cochlear implant would work, these would be artificial retinas that would send the visual signal to the brain. I don't know historically if these work as well as cochlear implants, but the future is bright. And yes, that was a really bad joke because light vision. All right, moving on. Talking about color vision. Oops. Sorry, my dog is here with me for the lecture, and I accidentally bumped her because I forgot she was there. So again, I tell you that till I'm blue in the face, that the similarities between the auditory system and the visual system are great. There is a lot of connectivity between them, which is why I teach them together, right? And things like that. So for the primary visual pathway, we had the LGN, whereas the auditory pathway had the MGN. Now, one of the things I also talked about in the last chapter was that there was a portion of the visual system, auditory system that goes through the midbrain, and it went through the inferior colliculus. Well, there is a secondary, or what we call an unconscious sort of pathway, which is more about knowing where objects are and being able to move your eyes in the direction without moving your entire head, and also contributing to what we call unconscious vision, which we'll get to later. And that goes through the superior colliculus. So just like we have the superior colliculus for the secondary pathway of the visual system, and we have the inferior colliculus for the auditory system. We have the MGN. I have an audition at MGN Studios for the thalamus, and we have the LGN right next to it on the lateral sides for the visual system. So even their pathways and everything are very similar. When we talked about pitch perception in the last chapter, when I talked about it and the book talked about it, so I give it the royal we, I talked about two different theories, one being frequency theory, which did a good job of accounting for the lower pitches, but not the higher ones. And I talked about place theory, which was really good for the medium and higher pitches, but really bad for the lower ones. And the bottom line for that, as a review, is that the combination of both was the best way to think of all pitch perception, high and low. Well, guess what? In the visual system, we also have two different theories because one by itself is incomplete. So two researchers, two scientists named Young and Helmholtz, came together and realized when they did research on the eye, they wanted to know what was responsible for color vision. They wanted to come up with a theory and be able to test it. So what they did was they looked inside the cones and they realized that there are three primary colors, kind of like what you think about in art that you started probably since preschool, right? The three primary colors that are represented in cones are red, green, and blue. So in this case, they talk about the fact that observers can't resolve these colors into separate components. There's a red, a green, and a blue, and it's the combination of inputs of red, green, and blue that make up all the other colors. So you may have a problem with this, or you may have noticed that if you compare it to your knowledge on the primary colors in art, you say, wait a minute, something isn't right here. What are those colors? Of course, this is the point where I'd ask you, what are the three primary colors in painting or in art? And red and blue are part of it, but wait a minute. Green is a combination of two things. Yellow and blue make green. I remember that there was the commercial that talked about yellow and blue make green, and actually to make sure that Ziplocs were closed, because a lot of times in the 80s and 90s, a lot of people thought their Ziploc bags were snapped shut, but they realized after there was some spillage that they were not. So this whole idea of yellow and blue makes green was a commercial that Ziploc made, which was pretty ingenious. I have no idea what that sound was just now. An email or something. That basically, to know that your Ziploc was actually locked was, oh, that's what it is. Apparently I have been automatically signed up for a Zoom meeting, which I'm not going to attend because I'm doing this. So that's what that notice was. Anyways, yellow and blue make green. So in order to know that your Ziploc bag was actually shut, you put the yellow side and the blue side together and it came out green. And if your whole strip was green, you knew that the bag was securely locked and it would not spill over. Why they ever got rid of that, I don't know, because definitely people could use that these days. Anyways, so there is a difference here. We have not red, yellow, and blue. We have red, green, and blue, or RGB. And by the way, if you've ever looked at the back of a projector or your TV or a laptop sometimes, computer screen, there is an input that says RGB. And RGB stands for red, green, blue, which is much like the cones in the eye. And so it seems to be that this combination allows us to see all the different colors, except it's incomplete because if you already have green and green came from something else, how is it that we can account for the actual color yellow? If these are the three components, right, the three primary colors, then you can't really account for the color yellow here because red, green, and blue are the primaries in this theory. So because you can't account for the color yellow, this is an incomplete theory and it has to be either refined or combined with another theory, kind of like we saw in the auditory system. And that is what we see here. Well, this is what we see in words. Apparently the picture is also not here, so I will scroll down on the other page and show you guys. Another man a few years after Young and Helmholtz, named Herring, also had a problem with this theory. He said that maybe it's not the cones themselves that are giving the input, but it's the ganglion cells. Remember, the cones are the ones that take visual information and turn it into a neural signal that the brain can interpret. But they give their information, right? The rods and cones, the photoreceptors, they send their information to the ganglion cells, and it's those ganglion cells' axons that form the optic nerve, and it's the ganglion cells that give information to the brain. So what Herring said is maybe it's not the cones, but it's how the cones project onto, remember this phrase, it's how the cones project onto the visual fields of the ganglion cells, because the ganglion cells are the ones giving that information to the brain. So Herring said, no, it's not the cones. It's how the cones project to the ganglion cells and how the ganglion cells interpret it. And what he said was the ganglion cells interpret this in an opponent process fashion, so that the red and green cone photopigment that is sent to the ganglion cell is broken down by red light and regenerates in green light. So in this case, red and green are opposite effects. We also have the same thing for yellow and blue. Yellow-blue cone photopigment, which is broken down in yellow light and regenerates in blue light. So basically there is an excitatory part of the ganglion cell receptive field and there's an inhibitory part. And if it hits the excitatory part, you'll see red. And if it's the inhibitory part, you'll see green, or vice versa in some of the other cells. Same thing with yellow-blue. This also is the same for black and white, which is why black and white are opposite colors. So this theory helps to explain yellow being a primary color when it comes to art and not in regards to the cone. It also tells us about complementary colors, browns and greens and things like that, orange being red and yellow. And it also gives us this negative color after effect. So in this chapter, And in my Psych 1 Myers textbook, there was an after image. If you saw a flag, there's a picture of a flag that is yellow, black, and green. And if we go by the opponent process theory, that when you stare at it for 30 seconds and then you stare at a neutral wall, like a white wall, you're going to get the opposite effect. So as you guys know, the stars and stripes, right? The stars and half the stripes are white. So those would be black in this image. The other stripes are red, so they would be green. And then, of course, in the area where the stars are is blue, right? So we have the red, white, and blue. So that would be yellow. And I will show you an example of this, and you can look at it on your own to see if it actually works. The problem with this is Herring's opponent process couldn't be physiologically studied. We can actually physically see the cones that accounted for RGB, or red, green, blue, but you couldn't see the effect of these physiologically transferring to the ganglion cells. So people were skeptical about this at first. Now, if I go over here to chapter 10, let's see, is it going to be down here? I don't think it is. It's going to be the next one. So give me just a second to allow my to color vision. So now we are getting to it slowly but surely. Thank you to my slow computer. And we can see here that this is the opponent process theory slide. So red and green, as you can see at the top is red, and on the opposite side is green. On the right side, you see yellow, and on the left side, just opposite that, is blue. And that's how these are explained. This also helps to explain, as you can kind of see down below if you're reading now and not paying attention to my voice, maybe a little of both, that this also explains color blindness. So if you weren't aware of this, the most common types of color blindness are red-green, where people have trouble distinguishing between red and green. So if you look at this slide, it's because there are ganglion cells that are specific for distinguishing between red and green. And if those ganglion cells are not, if we don't have as many of them, or if they're not working properly, then a person will not be able to distinguish between red and green. On the opposite side, going right to left, the second most popular type of color blindness, of course, is yellow-blue. So these people that have that type of color blindness are unable to distinguish between yellow, or gold in color, and blue. And of course, black and white, even though that's the rods and not the cones, those are opposite colors as well. And so what that tells us actually is we can now understand one of these things that broke the internet. And what I mean by that is, if we think about that issue from about 3 or 4 years ago called The Dress, there was a freak out by a lot of people, because some people saw the dress as black and blue. And if we think about the opponent process theory, what would be the opposite of black and blue? Well, the opposite of black is white. In the opponent process theory, the opposite of blue is yellow or gold. So think about it. And the video is also going to be posted below with some visual illusions. The dress was either seen as black and blue, or its opponent process of white and gold. And that depends on people's individual thresholds and sensitivities and you know, the inner workings of their rods, cones, and of course ganglion cells. So when we mix lights, mixing lights is actually additive. So looking at red and green, we see yellow. Looking at red and blue, you see purple on the left. We have blue-green, which is sort of an aqua color. And then in the middle, when everything's mixed together, we see white. Paints are the opposite. This is why it's a little bit different when we're looking at light versus like artwork that you did starting in preschool or kindergarten. With paint, it's subtractive. So red and green is going to be a little darker. Red and blue, you still get purple, but it's a darker one, not a lighter one. And if you mix everything together, you get a gray or a black. And that's why it's not the same as how you learned your primary colors and everything in art class. I just wanted to point that out, as did the book. So, the combined theories of the trichromatic, 3 cones, because we do, and we have seen this in physiological studies, we have 3 receptors. We have the RGB, the red, green, and blue cones, and it's the combination of those cones and how they project onto the receptive fields of the ganglion cells, yellow, blue, red, green, and black, white, that represents all of color vision and how we can distinguish among the different colors. So remember from the last chapter, we talked about frequency theory for lower pitches. We talked about place theory for higher pitches and medium pitches. The best way to account for all pitch perception, high and low, is a combination of both place and frequency theory, or frequency and place theory. For color vision, how we can account for, including the color yellow, all of the different spectrum of colors that we can perceive seems to be a combining the theories of the 3 cones, trichromatic theory, and how they project onto the ganglion cell, which is using those opponent process theories. So again, just like the auditory system, the visual system, the best way to account for wavelengths and hue and color is the combination of both theories. And because, again, the picture hasn't shown here, we can easily go back to the next slide, which is right here. Here's your combined trichromatic theory and opponent process theory. We have the red on the left, we have the green in the middle, and the blue on the right. And you can see the combination of green and red. On one side, positive will give you red, the other side will be green, and that's why you'd see it in an negative after effect. For green and blue, that gives us sort of the yellow-blue combination. And those are opponent processes. So, as I've written for the other class, I will say it here. Just like in the auditory system, where there are 2 theories of pitch perception, the best way to account for color vision in the visual system is the same. It is a combination of trichromatic theory, 3 different types of cone, red, blue, green, and opponent process theory, which states that we have 3 ganglion cell types that receive information from the 3 cones. One that responds in either yellow or blue, one that responds in either green or red, and as I talked about, black and white. So I believe that this chart is able to be seen. We just need to get to the next slide. And here it is. So we're looking at the blue-yellow ganglion cell, which is excited by green and red cones, and that will give us a perception of yellow. It is inhibited by the blue cone. So again, you will either see gold, yellow, or you'll see blue. The dress was either black and blue or white and gold. And yellow and blue, of course, are opponent processes. For green and red, we have excitation by the blue and red cone, which perceives red, and it's inhibited by green. So again, red and green are opponent processes, right? And black and white would be, remember that additive, we have all light. Light is additive and paint is subtractive. So all of them together will perceive lighter. None of them will perceive darker. So that's where we get our contrast of black and white, which we will talk about more in form vision in the next lecture. So looking for support, obviously we're always doing research and looking for support of theories, either one or the other, or support of the combined theory. And here we see, just really quickly, that we see peak responses in the cone receptors and paired ganglion cells in monkeys, which show us that the lower nanometers, right, again, going back to that wavelength, is more of a blue or purple. In the middle kind of a green at 534, and getting closer to the higher number, the more red we see. Just like in the auditory system, we talked about a tonotopic map, and that's sort of where place theory came in. Where it hits in the cochlea on the basilar membrane is adjacent to where it's going to hit in the auditory cortex. Well, for light and visual information, we have what we call a retinotopic map, which we'll get into. And in the retinotopic map, where it hits in the retina is adjacent to where it's going to hit in the visual cortex, in the occipital lobe. So, again, we don't have a picture here, but I can go back to where we were, looking at the combined theory. Let's go ahead and do that now. My apologies again. I guess we have to go to the next thing. So let's see if I can find it. Technical difficulties. Stand by, please. Okay, so I guess we don't have it in here. I'm going to check the beginning of form vision and just see if it was sort of snuck in there. I did talk about the retinotopic map, so yeah, I guess we're out of luck on this picture here, but it's I think it's just the same idea that some of the fields, the retinal fields, have complementary circles of cones, and the color opponent fields increase discrimination and contrast through something called lateral inhibition. The idea behind lateral inhibition, which I will explain more during form vision, black and white, is that when cells are excited, they inhibit their neighbors on either side of them. So if you have 3 cells next to each other, 1, 2, and 3, if 2 is excited, it's going to inhibit both 1 and 3. I will go through this a little more, and you can read about it a little more in the next lecture. So, really quickly, this is a test for color blindness. This also helped researchers understand color vision processes. So people who lack one or more of these cone types, right, are going to not be able to project as much into the ganglion cells because they lack that cone type. And as a result, if it's red-green or yellow-blue, you see color blindness. So the test for this that the book gives you and the slides is that there is a number that's in these little circles that create one big circle. If you can see the number on the inside, you don't have color blindness. If it is difficult for you to see the number inside this circle, then perhaps there is some sensitivity and maybe even a lack of cones. So when we come back, and now I can see that we need that picture again, I will do form vision and talk about visual agnosias, which is problems with the visual system that may cause us to not be able to interpret certain types of visual information. So please join with me next time. And as always, I will talk to you soon.